So we're delighted to have Patrick Kuhn, who will tell us about safe planning for robots.
Okay. Thank you, Yuba, for the gentle introduction. And hello, everyone. My name is Nakseung Patrick Hyun. I'm a PhD candidate student at Georgia Institute of Technology. And I'm very happy to present one of my work at Microsoft Research. And today, I'm going to talk about excuse me, the optimal safe path planning using polynomials from algebra to geometry. And I'll make sense out of it, what that means, algebra and geometry. So in general, I am very interested in the motion planning of mechanical systems. So motion planning could be a path planning for autonomous vehicle, like a Google Waymo car. Or it could be actually the periodic motion planning for the bipedal robots, so that it makes a stable walking. Or it's not actually restricted to the rigid body robot. It could be a motion planning of the soft robots, which can actually bend itself, deform its body. But those kind of problems is usually hard because it doesn't have a meaningful joints to describe the motions. And also it's not really restricted to the controlling the single robot, but it's also for the multi-agent robots, where the robots have its cooperative goal to make maybe a certain shape in the sky, like a V shape here. So in this talk, especially, I'm interested in talking about the optimal safe path planning. Safe means that there's always an obstacles in front of you, so the safety has to be assured by detouring the obstacles. How can we find those feasible paths? So once you have the set of feasible paths, we can now start talking about what's the optimal path among those feasible safe paths. So optimality can be another important property of the path planning. And so the challenge here is about, okay, every path planning problem has a first question: how are we going to generate the path, which starting from your initial point to your desired target position. In the course of navigation, we want to guarantee that it is safe. And the second, for the example, so in here, let's see that like there is a yellow circular obstacles in the scene, and this red path is like one of those feasible paths which actually navigate through the scene of the compacted obstacles. And like I showed you in the before slides, maybe the objective is having a multiple robots to make a certain shape. But the problem is, without having a central commander that assign, hey, robot 1, just please go to the target position 5. By just measuring the relative position of each other, can we actually achieve the goal of making a formation? So first thing is, well, you have to well define the meaning of what do you mean by the formation, and how can we understand in the multi-agent system. So there are some limited information. Limited information means there's no central commander, and we're just measuring, there's no communication channel, but we're just measuring the relative positions. Can we actually achieve the goal? And this is one of the results, which I'm going to go over through the slides. And so assuming that you have a way to generate the safe trajectories, now we can actually solve the optimization problem by, for example, minimizing the arrival time could be a very good one of your cost functions, or by minimizing the energy that you consume, minimizing the control effort. And so these are the questions that I'm going to go over and explain how our framework has been overcome those challenges. So as you guys can have seen in my title of this talk, there is two parts: algebra and geometry. And I'm going to use polynomials for both cases. The algebra, the part one is about the algebra. In here, we are only focusing on the point mass robot, assuming that robot is a point with the mass. You can think of that, it's actually a path planning of the center of mass of your robots. So what's the planning of your center of mass of your robot? That's the question. And here are some examples that is the result of our framework. And after that, by first finding a single robot optimal safe path planning, we actually now go for the formation control using the multiple point mass robots to make a certain form. In here, like we were able to make a V shape, but without assigning anything. So this is the 17 robots, which makes a V shape, but without assigning the special the target position to each one. And also this is like making a circle, and I'll show you how I get that through the slides. And the second part, yes.
Just to understand, like,
Please, yes.
so you just want to plan the safe path for multiple robots.
For the multiple robot is going to be the second bulletin,
Yeah.
and the first one is the single robot. Yes, but they're both actually coming from the very basic idea, which is the fundamental theorem of algebra.
Okay, but
The roots
assignment
aspect.
free basically means that you're not. There is no dictator who is studying.
There is no dictator. Yeah, there is no. That's a great question.
And the environment in the first case is known to the.
Yes. In
and
here.
the robot-
Hmm?
Yeah. Okay.
Please.
Okay. And the second case,
Hmm?
what like? I guess you'll talk about what they
Right.
can observe and what
Right.
they cannot observe.
Right,
And,
right.
Okay. How they know they're at the
Right,
but
right.
okay.
That's a condition for the information structure. What do you have in your hand? And in here I'll go more into detail.
Okay,
later.
yeah.
Right. But great question. Any other questions before moving slides? No? Great. Yes. Awesome. So in part 2 is a geometry. In here I'm not going to do the path planning for point mass robot anymore, but I'm going to actually consider the actual body of the robots and do the safe path planning. And particularly I'm interested in the rectangular shape of the robots or the ellipsoid or ellipse shape. So I'm going to do the path planning for the 2D and the 3D case, but to give a distinction to the part 1, as this part is I'm actually considering the body of the robot. And at the end, what we're going to find is actually the analytic equation for the surface. And then after that, we actually propose an analytic safety condition of the surface. So it will be very different from other sampling-based path planning method, which you actually sample your body or the space. So once I constructed those analytic safety constraint, and then I'm going to pose a general Bose type of optimal control problem, and after that I'm going to solve numerically the equation. Oh yeah, thank you. So let's start our journey. Algebra. The path planning, I think, a very simple question. It might be too easy for you guys. But how did we draw a circle? How do we draw a circle mathematically? Anyone? I guess everyone knows. It's an implicit function. X squared plus y squared is equal to 1, and the trajectory of that is a circle. Or even you can have an explicit formulation by having a parameterized curve. You can actually draw a circle. Or even you can actually solve the differential equation and and starting at the right point on the circle, then it's going to periodic orbit of that ODE. But our point of view is very different. I'll say that I think the trajectory on the circle is actually the smooth transition between the polynomials. By the Euler's formula, R2 space can be identified as a complex space, and you have an inverse too. And so one point on the circle is actually just one complex number. And say you have another complex number here, which is a conjugate pair, and that's another complex number. So say you have two complex numbers on the sphere, and that identifies one polynomial, which is s squared minus 2 cosine theta s plus 1. The roots is actually exactly the position on the circle. But it's parameterized at theta. So you have actually a family of polynomials parameterized by theta, such that if you were able to follow the roots of those smooth transition of the coefficients, then it will ended up generating some desired trajectory. So this is a motivating example. So okay, maybe path planning in 2D can be thought of as finding a smooth transition between the polynomials. But this idea is not new. What I meant by not new is, in control theory, we use this every time. It's so-called a root locus method. How many of you have heard of root locus method? 1, 2, 3, 4, yeah. I'll control that. And so I'll just briefly go over what the root locus method is. given a linear system, your input-output have a linear relations. The system can be described as so-called a transfer function. It's a complex valued function in a rational pole. It's a polynomial over polynomial. And we call the roots of the AS, which is in the denominator, as a pole, because when the roots are in there, the transfer function blows up. So it's a pole. And the roots of BS is actually, we call as a zero, because it kills out, it zero out the transfer functions. And the feedback control, the main essence of the proportional gain feedback control is by changing the right gain value k such that you move the pole from the right-hand plane to the left-hand plane. The objective is that if the pole is in the left-hand plane, your system is stable. If pole is in the right-hand plane, your system is unstable. So using the feedback control k, by changing the k value from 0 to infinity, you actually track the location of the poles of the closed-loop system. And the poles of the closed-loop system can be obtained by solving this characteristic equation. And I believe this is a golden equation to me for my path planning, because it hints the idea. So here's an example. Say your AS, original, have a pole here. And that's when actually the roots, when k is equal to 0, right? Just plug in k0, then this equation becomes AS equal to 0. By changing the k value, small and small and small, you can actually track the roots and see that it actually moves and moves and moves to the left-hand plane. And when k goes really, really large, it actually goes to the roots of BS, because this part is actually now going to be dominated. Think of dividing this with the k, and get k goes to infinity, then it's going to kill out this part. So to me, this is like a starting location of the robot. And this is my target position. So this is how easily we can actually generate the path for a single robot, starting from here and to go there. You just treat yourself as a pole, and you treat the target position as a 0, and then just follow the Locus path. But this has a limitation, right? Why? Because I only have one freedom, which is k, that moving on a real line. So I have to follow this line. It's forced by just solving this polynomial equation. So I rather look into the generalized rule locus, which is actually uncommon in control theory, such that instead of using the k as a real parameter, because I'm not doing the system theory anymore, I'm using the idea of characteristic equations to the path planning. By choosing the complex number k and varying the complex number on a ray on the complex plane with certain angle theta. So theta is fixed, and I'm just changing the magnitude of the k. So I'm moving on a ray on the complex plane for the gain value. And the trajectory now becomes like this. So I have another degree of freedom. By choosing different theta, I have a different path. But at the end, when k goes to infinity, all morphs down to the 0. So this gives an idea, okay, then maybe I can generate multiple paths. I didn't talk about the safety yet, which we're going to come shortly after. But this tells us the idea of how we can actually generate the set of trajectories that march to the target position. And since there's no requirement for choosing AS and BS, BS is, of course, has to be a target position, but my point is that AS can have a complex coefficients. So you can actually remove the conjugate part. You can actually start with the complex polynomial, meaning that the coefficients are complex now, so the roots are not going to be conjugated anymore. And it doesn't have to, that's what I meant. And so now we can have more freedom to designing the path by just placing multiple poles on the other location on the planar space. And the beauty and the great part of this generalized locus method is actually in the algebraic expression. Given the angle theta, which was a design parameter in here, it uniquely defined the angle of departure. So theta was not the angle of departure of yourself, but by just solving this algebraic, very simple equation, you can actually find the corresponding angle of departure of the pole where you want to start. And the angle of arrival are also uniquely defined by just one parameter, theta. So here's an example. So if I choose theta to be equal to 0, then I can just add and subtract those angle parameters to actually compute the angle of departure of this pole and the other pole, and it's uniquely defined. And so by having that, now the question is, I actually hinted out a little bit of what could be the path that go from your starting point to the end point, but I haven't discussed how I'm going to generate it, right? Because the roots of the polynomial does not have an explicit formulation using the just algebraic operation and the radicals if the order is greater than 5, right? That's Galois theory. And so we are actually aiming for finding not just explicit solution of the roots as of one parameter of theta or k, but rather actually finding a flow, differential equation, which ended up having the same trajectory. And this is the solution.
So I think I
Yes.
lost.
I'm sorry,
like,
yes.
I mean,
Please,
this is a
please.
different
Yes.
way to think of the problem. So how are you modeling the obstacles here in this?
They're not there yet.
They're not, okay.
Very good question, because I started with path planning, right? So
Yeah.
that's coming up in the 3 slides one. This is
Okay,
kind of
okay, so
overview to understand.
I just wanted to make
frame.
sure that I'm not missing
It,
some
will-
big
it
thing
will
there.
come.
Yeah.
It will come. We can promise. Any other questions? Yes.
In fact, I'm not familiar with the departure angle. If it is important to understand your work, could you explain it a little more?
Okay.
What
Okay.
is
I can do
departure
it.
angle?
Yes. So this line. Let's see. The red line represent when I choose theta equal to 0.
Mhm.
So on there, it actually as you can see here, there is a unique angle which can actually follow this line.
Yeah.
And that angle is the angle of departure. So by picking one theta, you find a one angle of departure. By choosing different theta values, then you have different angle of departure. Does that answer?
Sure. Yeah.
Great. Oh, we found out that there is a flow which actually generate this whole generalized through locus path, and wanted to understand how actually we can, because at the end for the robot, all I want to know is actually which direction locally I have to go with certain speed and the angle, right? I have a question. Yes.
So just on the previous slide, so I follow all this, but
Yes.
why don't I just follow the line from the pole to the root? Like, so why should I prefer a curve of this form as opposed to any other curve on this plane?
Oh, that's a very, very good question actually. Because at the end, I guess you're talking about like the general path planning problem. There will be many paths.
Yeah.
But why do we have to follow this path?
Exactly.
Because at the end, what I'm going to claim is that it's going to simplify the problem. The problem that you stated is actually the infinite dimensional problem. You have to find a function. You have to find your control functions, which generate the path. But in here, by having this all guaranteed safe path, now it's actually translating the problem into the finite dimensional problem of what's the best theta. So it's not the optimal solution, but what I claim is that it could be a good suboptimal solution of the coordinates problem.
And for one, the issue is, for one robot with no obstacles, there's no issue, right? But in the next slide, he had, 1 million robots or 100 robots, and then if you just have them go in straight lines, they will clash with each other. Well,
Yes.
here his method, because the roots are different, he ensures that the robots all gracefully avoid each other.
I like the word gracefully. Yes. So in the following section, then when you see the multi-robots, because multi-robots, now I'm going to plan it as each robot is the poles. And there's 100 robots, then you have the 100 order polynomial, and then do the robots. And you'll see some interesting animations. But it turns out that this flow is actually going into the gradient direction of some landscape function, and the which landscape function is actually, this is the harmonic functions that you can actually, following the gradient descent of this harmonic function, is actually equivalent to generating the whole set of root locus path. And so the good part of the harmonic function is such that the minimum and the maximum always occurs in the boundary of your domain. And the boundary is actually at the pole and at the zero. So starting from the pole, you're going down, flowing down, will not have a local minima inside your domain. So it's not stop, but actually keep going to the minimum point, which is at the other boundary at the minimum. But that's actually at the zero. So that's actually the convergence. And so the previous dynamics can be easily written in this form with the gradient flow of the harmonic function f. And as you can see, it is actually the asymptotic behavior. You don't arrive there in the finite time. You have to actually evolve this ODE or k goes to infinity. But that can be easily fixed by doing the reparameterization of the differentiable curve. Like reparameterize over the arc length parameter, then with the unit speed of the propagation, then you will arrive at the zero in a finite time, but you won't stop there because the flow at the end you will actually keep moving. So numerically, if you follow just the arc length parameterization, at the end, by the slight error, you just a little bit of fidget. Yes, please.
So, are you? I guess I'm a little bit unclear on whether you're considering the dynamics of the system as well, or is it more that you want to find the trajectory?
That's a valid question, and here's why. Because the dynamics of robots, of mechanical systems, you have to actually derive the equation of motion, right? By setting up the Lagrangians, and you derive the equation of motion. But in here, it's now the question, even with the control, actual control, if you are provided with a reference trajectory, can you find a controller to actually track those reference trajectories? So this part, for the point mass trajectory planning, is actually for finding a good reference to follow. So if your question was about, am I considering
a point mass?
Exactly. So that's going to provide you maybe a good path that you can follow.
Okay.
Maybe slowly. If it's unfeasible, then maybe slowly just try.
Okay. So okay, that's.
Yeah. But in the
So I should
yeah.
think about like you're going to use the poles and the zeros as like this is my start location, this is my end location.
Yeah, I'm going to use it like that. Yes.
Okay.
To generate the reference rate.
To generate the reference trajectory. And
Yes.
designing a controller on top of that is a whole other problem.
Exactly. But that will come on the second part.
Yeah,
In the
yeah,
second part, we're going to consider the actual dynamics or the kinematics of the system.
Okay. Sorry, just wanted to.
But no, but that's a very, very good question. Yes.
Should I worry that
Mhm.
this method will only give me smooth trajectories? Like, would I, in realistic situations, would I want non-smooth things?
Okay.
Like if I have a robot that's like,
Yeah, that's very interesting question because usually people want smooth rather than non-smooth. But if you want non-smooth, and yes, this actually just only providing the smooth curves. But that's a very interesting question. And non-smooth path can be usually actually by switching of the controls. So, any other questions? Okay, I'll move on. And so now the path time. Different. Okay, now here it is. So here's the rubric. Say that there is n-1 robot in the scene, and you properly place the pole nearby on the boundary of the obstacles, and you place a pole on your starting point, and you put a 0 with a multiplicity of n. N is the total number of poles. So I'm matching the pole number of poles and zeros in this scenario. And then pick theta such that your favorite theta, or try with many other theta. And here is the result. Say your triangle is a robot, and this black circle is your target position. By having every different theta, then you will end up having here what you're actually surrounding some of the regions, which is the region created by the poles in the obstacles. So if you can place your obstacle properly inside those regions generated by the poles, then all the trajectory here will be a safe path because the Locus path does not intersect to each other. It's a partitioning actually the space. And so
So on the right side, we see the obstacles clearly
Right.
in the path.
right.
The left side, where are the obstacles?
The pole is in here, so any obstacle any obstacle that can be inside those regions, which I call it as a shadow region, then it will be the safe. If not, place more poles on the obstacles, then it's going to actually enlarge the body. Or you can play around by increasing the order of the poles in the obstacle. That's also going to be enlarging the body of the shadow zone. And the analysis of the shadow zone is actually not here, but I think it's important, and that's where I actually met Yuval on his talk, that he did a fair allocation on a sphere, and he actually measured the area on the Bezinov attraction, and those actually we are actually solving the same equation, where he only have a pole, not zeros. But he was able to compute the area of how far, what's the area that the one pole can cover. So it's very interesting. And yes, please.
So how do you know where to place the poles, or how many poles to place?
Like
I could just place
yeah,
a lot of
that's
poles.
yes, exactly. That's a little heuristic at this point on where to put the pole is. But like I said,
Isn't it part of the input?
Hmm?
The poles are your obstacles.
poles are the obstacles, and your robot is also the poles.
Yeah, so isn't it part of input or?
But how many poles to put in an obstacle varies depending on the size of the
It really
obstacle.
depends on the geometry of the obstacle. How does it really look like? And so, still a many open questions. But the benefit of this is the cost is very free. You just solve the ODE, then you ended up having a good. And so, what I meant by it's good is that the original problem, without considering the dynamics, by just having a very simple, completely controllable system, that minimum time problem with some speed profile, say maybe you have to slow down when you're close to the obstacle, if you have a constraint like that, and you have a safety constraint that at any time you don't want to be in a collision or inside the obstacles. So this type of infinite dimensional problem can be easily reduced, but not equivalent, I'm claiming. You can actually formulate it such that it is actually changed it to the parameter optimization problem. So it's easier to solve and faster. And the speed profile can be easily multiplied by the normal flow of the Locus direction. And so here are one of the results that these are the multiple paths which generated by the Locus, starting from here, and it ends at there. And so if you let your speed profile to be 1, the minimum time problem is the minimum length problem. So you can find the minimum length solution among those feasible set that I have for the optimization problem. And if there's a profile that you have to get close, you have to slow down when you're nearby the obstacles, then the optimizer actually find the other paths, which is longer, but it is faster. This was part 1. And this is now, I'm jumping onto the multi-agent system control. So here's the objective. Let's say, so I'm interested in 2 types of problem. Yes, please.
So in the previous one, can I reuse solutions if my obstacles are moving around but very slowly? So I'm thinking of situations where I'm just
online planning, right?
Yeah, exactly.
You're thinking about the online planning.
Yeah.
That's a brilliant question, because right now I was considering the offline planning, but online you can actually update the location of the poles and you can resolve it. Or it's like moving horizon. What was it? Model predictive control. You evolve and resolve the optimization each time at a different problem, and that's actually part of the work me and Yuval did over 2 days ago. But not single robot case, but the excuse me, the multi-agent system case. Yeah. Any other questions?
What do you mean by you can do it online? Like
So online meaning that because in here I'm assuming that the obstacle is not
yeah.
changing. So
But what do you mean by you solve it online? How do you
I can frame the problem or the algorithm as to handle an update. Update meaning that it's
Change
time variant of the scene. And then we retreated maybe the robot, moving robot of the, or as another pole. But now it has, since it has a new location, we don't follow the previous ODE, but we create another vector flow, which we can follow. Yes.
So, I guess, in what situations would you recommend using this algorithm over, say, RRT star?
I will recommend this one to actually define the topology of the feasible trajectories. Topology by means that from going here to here, you can actually pass here, 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 and here. So I was more thinking this as not actually the reference trajectory, but having a good initial guess for the optimizer for the next one. So this will be just the optimizer of my trajectory that I know it's safe. And then from there, I can start considering the dynamics and the safety conditions to optimize. I could use the same method by using the RRT as generating one of my feasible path solution. So I'm not claiming that like which one will be the better one,
But with very few, if you had
Yes.
very few poles,
Mhm.
wouldn't this be faster than RRT star because or would
It-
it not?
it could
Because
be.
you just like if you're just solving
Exactly.
if you can solve
RRT,
this equation
you have
fast,
to, right.
um,
I honestly have not considered the comparison of the computation time of the other sampling-based method, but I think it's worth looking. Definitely, yes. Any other
Now
questions?
that you mentioned computation time, actually what's the running time of this algorithm? It's just, how do
Oh.
you solve those equations? Just
Oh.
discretize it and do a flow computation?
Yes, that's very good. It's I just all the simulation is based on the MATLAB and solving the ODEs here, but I think I could answer better on the tools that I use for solving the optimization, where I use the in the next section. That I have a
Yeah.
slides for the numerical algorithm on how I solve the optimal control problem. Can I? Yeah. Okay.
Yeah, maybe we should save some questions for the end.
Yeah, that might be wonderful. It's always good to have many questions in the. So in here now the goal is that okay, let's say the birds. Birds may make a form while flying, right? But not at the particular position. So it's the goal maybe is that you don't care about where you make a form, but you have to make a form. And the condition also is that I don't care which bird to occupy which part of the V shape, but actually let's make a form, make a form. In other case, I actually want to go to a certain tree and then make a form. And in that case, I call it as just only the permutation invariant formation control problem, and the other is a translation and permutation invariant problem. And I'm going to use the same Locus method that I use for the single method. And so here's an example. I think you're all smart people, so I think you probably have an idea how to implement this. So before I have the zero has a multiple, the multiplicity greater than 1. But in here, I'm actually having a multiple zeros in the scene and treating that as my target points. So here's an example. There is a two poles here and there. By agreeing that we both robots are going to use theta 0, then this robot is actually flowing into this target, and the other robot is flowing into the other target. And you can actually switch the roles by choosing different theta. Then this robot actually now goes to here, and the other robot goes to the other target. But the point is that every target position is occupied at the end. So which means the formation will be reached. And that gives the idea of, but the problem that could happen is actually the star point. That's where your polynomial as plus k e to the j theta bs has a multiple root. Because the root itself, location is the robot's position. Multiple roots means it's a collision. So how many times does that happen? Then that point is called a breakpoint. How many times does that happen is actually, it's a finite number, 2n minus 2. So by choosing the theta angle, by avoiding the theta can be varied from minus pi to pi, it's continuum. There's so many of choices. By just avoiding this very particular 2n minus 2, you're always going to reach to your target position without colliding. And that's the basic idea of this formation.
And I asked this before, but the breakpoint is the theta or the SB? You see
Uh,
2n minus 2
So
breakpoint,
it was actually the SB,
so
the
the
point.
number of bad points. So how many bad thetas do you have?
How, it is upper bounded by the 2n minus 2 because there only exists such a point on the space that it occurs.
So it could be smaller.
It could be small, yeah, definitely, yes. And so, but in here, interestingly, I'm not just using any type of polynomial to describe the scene, but better choose a right one, which is, we call it as a configuration space. That's a subspace of the space of polynomial with where the highest coefficient does not disappear. And the condition is that the first coefficient, the coefficient of the n minus 1 order has to be 0. What does that mean? The sum of the roots are going to be 0. And so, which means the sum of the roots is actually the center of mass position of my deployment of the robots. So having that as my setup, choosing that as the polynomial in this configuration space, my center of mass is always at the origin. And there is an invariant principle that we also show that while doing the root locus method, the center of mass position is not going to be changed if I choose AS and BS from those configuration space. Because root locus is actually simply the linear combination of AS and BS. No matter which scalar multiple you actually multiply with BS, if you sum it, the coefficients at A1 is always going to be 0. And so the root locus actually preserves the center of mass position. And therefore, here's the problem and the solution. The target position is here in the global coordinate, which robot does not know. Let's say he does not have a GPS or map. And the robot's, the global coordinates is given by Rn, R1 to the Rn. And what robot can see is actually the relative position, the subtraction of those two, this vector he can observe. And by adding all those input signals from all the other robots, what you can have, and then average it over 1 over n, then you can actually have a vector coming from your center of mass to yourself. So which means you are able to actually compute the S1 in the root locus method. And by doing so, using the root locus controller that I propose, all the parameter here is actually a known parameter, and it's actually obtained by the current measurements. And so, and also to go to the specific tree, let's say all the robots are agreed on the center of mass of the tree, and let's flow there slowly all together. And this is the result. So this is the translation and permutation invariant solution. And all the X mark is the initial position of the robots. And by flowing this control scheme, and when we choose theta to be minus pi over 4, then this is the occupation and the trajectory. As you can see, visually prove that the collision has been avoided. And by changing the different theta, you actually switch the assignment here. So you have a freedom in your model too, for if you don't like this assignment, then you can actually switch by choosing different theta. And yes?
Sorry. The configuration space scales with the number of robots?
Scales the number of robots. Oh, thank you. It's very important to match the number of robots and match the number of targets. This is which means that the order of AS and BS has to be equal. If it's not equal, then one of the robots could go to infinity. That's where that's when there's more poles than zeros. But in here, we're considering we have a same n and number of n. Yeah, I should have mentioned.
So if you make more zeros and poles, you will gain a robot that will join you from infinity.
Yes, infinity. But having a Riemannian sphere, you can actually combine it on a sphere on Earth. But anyway, so this is the result with the translation also. The intersection looked like collision, but it's not. It's actually passing at a different time, so it's actually not a collision. And here are some results. With the 100 robots, I could actually make a circle without assigning. And to do the assignment, usually people uses the Hungarian method that takes I think n log n of the computation time. But in here, I didn't actually compute that. I didn't use my time to actually compute the assignment, but rather just you take the flow, and it's guaranteed that everything is occupied. And that's a letter making P, which is my middle name initially. I thought of making MSR here. That might please you guys better. But anyway, so that was part 1. And if you guys have a question, I'm more like to talk on the offline. And so I'll jump into the geometry part. So I always like to start with the motivating examples. Now here's the example that I want to solve. Optimization problem. Considering the kinematics. That is like the differential robots, the unit cycle model. And say that the obstacle is a square, and your robot is also a square. Then what's the safety constraint? How can you write mathematically the safety constraint? Is such that at every time your body should not intersect with the obstacles, right? So the most popular way of dealing this type of problem is actually by using the Minkowski sum. You start with the non-point mass body, but actually you have a Minkowski sum of your obstacles and the robot to make the problem a point mass problem. So you enlarge the robot by adding those things. So now this is the equivalent problem.
So you enlarge the obstacle, not the robot.
Enlarge the obstacles, yes. Enlarge the obstacles. And so now we're back to the point mass problem. But now, what's the safety condition? Now let's write the safety condition for this point that does not going to be inside the square. You can write it in with the constraints, but the problem is the or. You need an or condition on your constraints, which is analytically intractable that was given. So many of the research on first formulating this type of problem analytically relying on introducing the integers. You actually assign a slack variable, binary variable, to each one of the faces. 1, 2, 3, 4. So they require 4 integers. And solve the mixed integer programming, then you can actually find the path. But now, that's all. Integer programming is always backfires because we know that it's NP hard. So as you increase the number of obstacles, then the number of integer that you need is also increased. So major effort from I think the group in the Ross-Tedrake in MIT, they try to reduce the number of integer as much as possible to simplify the scene, and I think it's a really great work. But still, it suffered from the integer program. So we had an idea.
So one quick comment,
Yes.
that when you to take into account the geometry of these obstacles, you enlarge the obstacle.
Mm-hmm.
So if I had asked for a shortest path, then
Mhm.
this would actually change the solution, right? Because you're now.
This is not, so shortest path of what? Shortest path of the center of mass trajectory. So this problem was formulated such that I want to define
Yeah.
length of the path as the trajectory, the length of the trajectory of my center, right? Because now you have a body, so.
But your path itself depends on how you're representing these obstacles.
Yes, but I believe the formulation will be equivalent, though. The length, okay, I understand. So with this enlarged space,
Yeah.
the length in there does not meaning the length in the actual
Yeah.
space, right? But actually it is equal. I can go more detail.
Okay, yeah, we can take it
Yeah,
off.
yeah. Do you have a question? Yeah, so the idea that what we have is that, okay, why don't we just have those boundary? What's the equation for that boundary? I mean, to me, it looks like a L infinity norm unit sphere. Yeah, it was not obvious at the first place, but L infinity is a max norm, which means it doesn't have actually a gradient at the corner. So how about let's choose an LP norm and choose the P something really big. And that would be similar to a square, but it's going to be a smooth manifold. And so here's the different unit sphere of different choice of P. And this is the equation of the weighted. Weighted by means, I think everybody know what weighted means here. And so And it is interesting that as p goes to, I think the farthest part was, I think, 20, I think. No, I think that was 10. 10 was the last one. And as you increase, you actually get closer and closer to the actual geometry of your robot or the geometry of the obstacles. So and this is it actually can work it on the 3D case. You can choose a big P to actually model a cuboid shape as well. And now what type of collision that it can happen between the two rectangular, the two robots or one rectangular robot with the rectangular obstacle? There's only two cases actually. So that's why the planner is very simple. There's either it's going to be the edge to the vertex collision or the vertex to the edge collision. If you can capture those two cases, then the safety is guaranteed. And therefore, the first, by transforming correctly onto your center of mass of your robot and rotate it, because now your robot actually have an orientation, right? So, and doing that, you have actually the distance function, which respect your geometry of the shape. And if you can evaluate the LP distance of each corners and say that it is greater than the 1, which is it's outside of my unit sphere, then it is safe. So that's 4 constraints. But the important thing is it's all connected with the AND operator. So I don't need an OR operation anymore for connecting those constraints. And do the similar thing in the obstacle geometry. In here, the P is different and the half lengths of these rectangles are also different. But by considering the inequality condition for the corners of robots to the obstacles, I have 4 more. So with the 8 inequalities, that I can actually generate the safety condition. Do you have questions? No. And circular robot is actually even much simpler. This is the actual Minkowski sum, and those Minkowski sum can be actually approximated by enlarging not the obstacle, enlarging your robots, and avoid the center of the circle of the obstacles. So it only requires the one inequality constraint for the circular obstacles. And by putting in here, then now we formulated a general Boza type of optimal control problem. And now the question is, how are we going to solve this? We're probably not going to solve analytically with our pencil and paper, right? So in here, well, what we choose as the numerical solver is the Optragen plus the iPod. The Optragen is a translator. It's a translator. Anything you symbolically written as a optimal control problem can be approximated by using the spline approximation of your continuous functions. So there's now only the control is the coefficients. Plus by using the so-called collocation method, sampling your trajectory and then sampling the time of the collocation time and at each collocation time, it must satisfy all the constraints. Dynamics, say holonomic, non-holonomic constraints. And after that, it actually becomes the finite dimensional problem. But it's going to be highly nonlinear. But so the point of the Optragen is actually the translation of the continuous, the infinite dimensional problem to the finite dimensional problem. Once you have the nonlinear programming problem, then we choose the interior point method and the solver to actually solve those NLP problems. And this is the result. So it was very nice. It was actually, it was very, very, very nice that this was a skinny robot. So I have the orientation. I only go through the shorter side of my body. Then it could actually clear the gap here and then reach to the final goal. But if my orientation is on the fat side, then I cannot clear the gap, so this optimization actually finds a detour. Yes, yes.
How long does it take to solve?
I have to remember. It's gonna be less than 2 minutes. Yeah.
Less than minutes.
Yeah.
Okay.
But yeah, oh, yeah, please. Yeah.
No, indeed, it's very nice, but you said that the previous approach based on integer programming was NP hard.
Mm-hmm.
But now you're using non-linear programming. I mean, that's also NP hard, right? are there any assumptions which makes it polynomial time?
Mm,
Or you think that it's just a better method among the two?
that's a good question, and also the question that I want to answer.
Okay.
But the thing is that the
I mean, you
I think
don't have
it's
to
I
answer
think
now.
what we're proposing is a new framework. I'm not trying to say that
Yeah,
we're
yeah,
going to replace
okay.
the algorithm, right? So having a good combination of the analytic expression of the safety plus the integer, I think that would be the
No,
best.
it's great, but I'm
Yes.
just asking whether this nonlinear
Yes.
program can actually be solved in polynomial
Yeah,
time. because
polynomial
of-
time.
Because we have some special constraints. or
Right. That's actually one of the to-do lists that I really
something.
want
You
to
don't know
really
this
want
problem is NP hard.
I do not know if this problem is in here. Yes.
So, I mean, 2 minutes to me seems slow. How would you change this? I mean, you know, you want to do it on a drone that's flying through the trees.
Yes.
You don't have 2 minutes. You have milliseconds.
Yes.
So what is the? Is there any
Mhm.
hope
Mhm.
to do that?
So that's a great question because as I shown in the first one and the second one too, I was actually thinking of doing the offline planning first, not the online yet. And this is what we present here is actually the idea of the framework, where the RRT or the fast method was very long time. People optimize the computation, optimize. But I think this could be the good start that we can, okay, now we have this formulation, let's try to optimize the computation. And I think that's one of the right direction.
I mean, this is on Georgia Tech computers. Here it would be second.
Yes.
But on a small
It is-
drone,
it is
you have
recording, right?
the equivalent of Georgia Tech computers.
Yeah.
Same
And-
computer.
This is all futuristic.
Yeah.
Yes, and I'm very excited to show the following slides,
Okay, yeah.
which is the generalization of my approach. So in here, what I assume is actually the fixing the collision type. I actually specify the type of collision, so that's why I have to check the safety of the corner and corner. But what I actually want is actually the closest point. So, and this is needed because if I want to extend this algorithm to the 3D case, now I was talking about 2D, right? But on the 3D case, it's not just a collision of like this type. You could collide the edge to edge. But look, all the corner points are safe. So if I used my previous method, it's not going to capture the edge to edge collision. But actually what I want to find is actually this point, which is the closest, respecting the geometry of my ship. So we actually propose, it's not published yet, but it is submitted to the transactions, that we formulated as a two-stage optimization problem. Why we could pose this as a two-stage optimization is because now we have analytic constraints. So since we have a smooth model of the surface, we have a two-stage optimization. I mean, it's mathematically really good, but how are we going to solve it is a question. And so we solve it. We actually solve the inner loop optimization analytically. We derive the necessary and sufficient condition for what the closest point could have analytically. So it's actually the implicit function as a function of V bar and all your state and orientations. But at the end, it's actually less than 8 inequalities. I have 4 equation constraints, plus the 1 additional inequality constraint, then I have a 3, and which already works. That this was the initial point, that it actually, the objective is to minimizing the center of mass trajectory, the length, and it actually rotates in the beginning, and then it actually detour, and it actually do like an edge-to-edge collision sliding, because I wanted to minimize the length, so it's better to get closer to the obstacle. And the safety the four equality constraint and 1 inequality constraint, which I didn't show, is basically actually a geometrical constraint, such that the closest point, the normal direction of your surface, has to be aligned with the normal direction of your cost functions. I mean, that's basic thing in the optimization. And also the safety condition is excuse me, it has to point at opposite, because the maximum will be pointing in the same direction, minimum will only pointing to the opposite direction, which I can go over offline.
The robots and obstacles are here convex.
It's convex, exactly. You made a really nice point because of my next slide. So now I'm considering the non-convex body, which is the bendable robot. like your finger. But now the question is, how can I model the surface of the bendable structure? Do I have an analytic equation, implicit equation, which the Lego set is indeed? Because all the self-robot, not all, but most of the self-robotics research is actually discretizing the surface. They don't look for the analytic formulation of the surface, but rather using the finite element method or just sample with the spring and mass. That's how they do. But I think we have a different idea of actually modeling the surface of bendings. And by controlling now the curvature, where we get this idea is actually from the same weighted LP norm, but not on a Cartesian coordinate, but we actually try to see what happens if we put a LP box on a polar coordinate. And construct back that into the Cartesian coordinate, it was naturally going to bend. And in here we have another parameter, kappa, which is the curvature. So by continuously controlling the kappa, we can actually start from this type of the bending to the other type of bending by flattening out and then getting rebended again. And this actually had an extension also for the 3D as well. And this is just that was my last important slide. And so just the take-home message is that for the point mass planning, it's possible to just following the routes that you can easily generate one of the reference trajectory. And also for the rigid and soft body, if you have, you can actually use the weighted LP norm to actually describe the safety condition. And I wanted to use this time to acknowledge my advisor and co-advisors and this work was supported by the NSF panel. And all the reference that I made can be found on the Google Documents that in this address. So if you're interested, you can follow this. And thank you so much.